Hello everyone, Mr. Fawcett back with part 2 of our derivatives and graphs of functions lesson. In the first part of this lesson, we came up with 4 relationships between derivatives and the original function. And we wrote them down specifically right here, but we're going to use those relationships to answer some practice problems today. And we'll talk more about those. If you missed those relationships, I encourage you to go back and watch part 1 of this lesson. But we will, of course, review these relationships as we're working through these problems, but you may just want to give yourself a refresher off the bat. So the graph of the function g of x is given below. Use it to determine the characteristics of the graph of g prime of x for the given intervals. You will need to justify your answers. You may assume that g of x is defined for all real numbers and continuous over its entire domain. So while in part 1 of this video we were looking at the derivative of a function at a specific point, now we're going to be looking at what's going on with the derivative over a certain interval. So maybe the derivative is positive over an entire interval of a function, or maybe it's negative for an entire interval, rather than just saying it's negative or positive for a specific point. So the first question says, what is the interval for where g prime of x is less than 0? So this gets back to one of our relationships. When will g prime of x be less than 0? I'd encourage you to pause the video, think about the answer to that question, and then if you know when g prime of x is less than 0, try to look at the graph and think about, okay, over what interval or intervals would the derivative g prime be less than 0? Okay, so one of the relationships we talked about in the first video was g prime of x is less than 0 when g of x, or the original function, is decreasing. Okay, so we need to look at places on the original function where it's decreasing, and then we'll know where the derivative is negative. Well, we have an interval from -4 down to -2. The function is decreasing on that interval, and it's decreasing from 1, well, all the way to positive infinity, right? It said g of x was defined and continuous for all real numbers, so we can assume that this function is going to keep going. So we're going to write those intervals. We're going to use open intervals because there's something special actually that's going on exactly at the point x equals -4. But between -4 and -2, we can say that the function is decreasing and the derivative must be negative or less than 0. So we have -4 to -2 open interval. And because we have another interval, we're going to use this u, which really stands for the union of these two intervals. So the first interval, union this second interval from 1 to infinity. So those are the intervals on which g prime of x is less than 0 because g of x is decreasing. Okay, now we're going to look at where g of x, or g prime of x, is positive. So g prime of x will be greater than 0 when g of x is increasing. So we are increasing along this interval. We are increasing along this interval. So we have two intervals here where we are increasing. The first one is from -infinity to -4 open, union, because we have another interval, -2 to 1, also open. Okay, so we've covered most of this function, right? For the most part, this function is either increasing or decreasing. But there are some points that we haven't talked about yet. Namely, right, this point right here, oh, still on my eraser, we have this point right here, this point right here, and this point up here. We haven't included those in any of our intervals, so we still need to discuss what's going on. if we come down here, we need to figure out the values for which g prime of x is equal to 0. So think about, again, g prime is our derivative, which represents the slope of the tangent line to the graph. So where would the tangent line have a slope of 0? What would the tangent line have to look like if it has a slope of 0? And the answer to that, right, it's going to have to be a horizontal line. That's where it's going to have a slope of 0. And at each of these points, the tangent line is horizontal. So at x equals -4, at x equals -2, and at x equals 1. At all three of those points, our derivative is equal to 0. Now, it doesn't ask us to determine which of these are relative minimums and which of these are relative maximums, but we can quickly talk about that now. This point up here at x equals -4, again, I would expect you to pause the video for a quick 15 or 30 seconds and state which ones of these are relative mins and which ones are relative maxes on your own, and then come back and see if you're correct. But this one up here would be a relative max. Again, it's a relative max because the function is increasing and then decreasing. So it's coming up, and then it's coming down around that point. So that point at the top is a maximum point, not a minimum. Down here, we have a relative min because we're at the bottom. Relative minimum, we came down, and then we went up, so that point is the lowest point of that section of the graph. And our final point right here at x equals 1, that is also going to be a relative max because we are coming up and then we're going down. So our function's increasing, then it's decreasing, which means our point when the derivative is equal to 0 is the highest point of that section of the graph. Okay, let's move on to our second practice problem. And we're going to come down here to number 4, where we're actually going to have to sketch a graph based on certain criteria. So you're going to draw a graph of the function h of x that fits the following criteria. Note that you will have to label your axes correctly. So read through the criteria A through C, and while there may be many different possible answers as far as correct graphs go, there will be certain things that everybody has to have in whatever graph they draw. So take a few minutes to do that and then compare your graph to the one that we worked through and see if it meets that criteria. Okay, so the first thing it says is h of x is defined and continuous for all values on the following interval -4 to 10. So we have a graph that is continuous from -4 to 10. Does not have, the axes do not have to be drawn to scale, but you do need to label -4 and 10. It says that h prime, so the derivative is negative over the following interval, -4 to -1. So I guess I'm going to need to label -1, and 5 to 10. Okay? And it's positive, the derivative that is positive over the following interval, -1 to 5. Okay, so think about what it means for the derivative to be, think about what it means for the derivative to be negative, right? That means our original function must be decreasing. So our function has to be decreasing from -1 to 4, and it doesn't say how it needs to be decreasing. It just needs to be decreasing. So -4 to -1, and from 5 to 10. And then it needs to be increasing because the derivative is positive from -1 to 5. So I'm going to put a point up here because it is defined at -4. And then the function needs to be decreasing to -1. It's got to be increasing from -1 to 5, and then decreasing again from 5 to 10. So I'm just showing you that 5 should be a relative max. Let me make that point a little better, because 5 is where it changes from increasing to decreasing. And -1 should also be a relative extrema. In this case, -1 should be a relative minimum. So your graph could look something like this. Let me just label those. So we should have a relative max here and a relative min here. Maybe your graph looks a little different, right? So let's erase this. Let's draw something else that could work. I'm going to leave those points there, actually. I'll just draw something different in between them. So it doesn't say that our function has to be a curve. Our function could be a linear function on those intervals. So I could have something that looks like, oops, still on my eraser. I could have something that looks like this, right? My function is still decreasing from -4 to -1, as well as from 5 to 10. And it's increasing from -1 to 5. And it still has those relative mins and relative maxes at -1 and 5, respectively. So many different ways you could draw this graph. Just make sure you have those key things labeled in there that you should have. Okay, time for our last problem, or two. Let's see how many are on the last page. Just one, but it looks like a longer one. A couple of different parts, actually. So we're given the graph of f prime of x. So let's make sure we label that properly. This is f prime, not the original function. It is the derivative. We need to use it to determine the key characteristics of f of x. And then we will need to sketch a graph of f of x right here. So eventually this will be our f of x, the original function, because we have already been given the derivative. So let's take a look at these questions down here. So we need to find the intervals where f of x is increasing, where it's decreasing, where it has a relative minimum, where it has a relative maximum. And then it asks us to find the equation of the tangent line to the graph at x equals -1. So let's see, I can squeeze, okay, good. I can squeeze all of these questions in here. Maybe make it a little smaller for us. Oops. Okay, so everything's in here except the equation of the tangent line question, which we'll get to at the end if we have some time. So the intervals where f of x is increasing. Again, we have to go back to our derivative and original function relationships. If the original function is increasing, that means the derivative must be positive. So we need to look at the intervals for where f prime of x is positive. And we see that it's positive on this interval right here, -2 to 1. We're going to use our little union symbol because there is another interval where it's positive, and that is from 3 to infinity. We don't include -2, 1, or 3 because the derivative is not positive there. It's equal to 0. Those are the zeros of the function. Okay, let's see the intervals where f of x is decreasing. Well, if f of x is decreasing, that means the derivative is going to be negative. So I'm going to do this in blue. We have -infinity to -2, union 1 to 3. So those are the intervals on which the f of x graph will be decreasing. Question 3 says the values for where f of x has a relative minimum. So this time we have to look solely at the derivative graph to find the relative min or the relative max of the original function. Now, there's one thing we can look at. So the derivative cannot be positive or negative at a relative minimum or maximum, right? If we're looking at a relative maximum, right? The derivative at this point is going to be equal to 0. Same thing if we have a relative min. Now, it doesn't actually have to be 0. We're going to get into that in other lessons, but for now, we're going to assume that the derivative is going to be 0. So let's identify the spots on the derivative graph where the derivative is equal to 0. Well, we have this point right here, this point right here, and this point right here. So we have 3 possible options for a relative minimum. But some of those may be relative maximums, right? Because we don't know. Just knowing that the derivative is equal to 0 doesn't tell us that we have a relative max or relative min. It just tells us we may have one of the two. So if we come over here to our relative maximum, right, our function is going from increasing to decreasing for a relative max. Now, what does that mean the derivative must be doing? Well, if the original function must be increasing and then decreasing, our derivative must be then going from positive to negative. So let's come over here to our f prime graph. At which of those orange circles that I use them to circle the zeros, at which of those zeros is the derivative going from positive to negative? Well, at x equals -2, it's going from, it is not going from positive to negative there. The only place that it's going from positive to negative is x equals 1. So x, and we said this was for relative max. So x equals 1 is our x coordinate for a relative max of the original function. The relative minimum, where the derivative goes from negative to positive, is at x equals -2 and at x equals 3. Okay, so we have a bunch of characteristics written down for the original function. Now we just kind of have to build a graph and fit these characteristics in here. So take a minute or two, see if you can sketch a graph on your own that incorporates all of these characteristics that we've written down. Okay, so I just put a possible graph up here and then we can talk about it. So let's make sure it fits each of these requirements. First one is f of x must be increasing from -2 to 1 and 3 to positive infinity. So let's check that. -2 to 1, that checks out. This graph is increasing. And from 3 to infinity, that also checks out. Okay, so it's increasing over those two intervals. It's decreasing from -infinity to -2 and from 1 to 3. Okay, so that works out. It has relative minimums at -2 and 3. So -2 relative min, and at x equals 3 also a relative min. You should be saying relative. I'm just out of space, so I'm just abbreviating min. And it has a relative max at x equals 1. Okay, so our graph fits all 4 requirements. I would encourage you to do the same thing with your graph. You can just kind of label it the same way I did to make sure it checks out. If it doesn't, go back and think about how you could switch it to make it work. Okay, the last thing we're going to do is, I'm going to leave this up here, I think. We'll see if we have enough space. Okay, so the last question asks us to to rate the equation of a tangent line at x equals -1. And it tells us that f of -1 is equal to 1/2. So again, we're building our equation, right? Y minus y1 is equal to m times the quantity x minus x1. So we're given our y1, we're given our x1, and we just need to find our m, or the slope. Now, again, this key relationship about derivatives and tangent lines. A derivative is the slope of the tangent line. So right here, this m is a slope, and this entire equation is the equation of a tangent line. So m is the slope of our tangent line. So if we can find the derivative at x equals -1, we know what the slope of our tangent line is at x equals -1, and we know what our m is. Let's take a look at this graph. Does it tell us what the derivative value is at x equals -1? Well, fortunately, it does. That's one of the points that's labeled. So f prime of -1 is equal to 5, and this is our m. So we get y minus a half is equal to 5 times a quantity x minus -1, which would be x plus 1. So this would be the equation of our tangent line of the graph of f of x at x equals -1. So we'd have, this would be that tangent line we were finding the equation of, right? And it clearly has a positive slope, which is good. And while it didn't tell us that we drew our graph before we knew that f of -1 was equal to 1/2, we could just label this now as 1/2, which would make that red point have coordinates of -1, 1/2. Okay, this has been the end of this video. I look forward to seeing you back for a new lesson next time. This is Mr. Fawcett. Enjoy the rest of your day.